Much of the recent progress in electronics has come from new manufacturing methods for miniaturizing components and circuitry. The changes have been dramatic ones.
This early IC is the equivalent of 4 transistors. One of today's microprocessor ICs is the equivalent of 50,000 transistors.
But along with this large-scale integration has come a problem. Newer ICs, particularly the metal oxide semiconductors or MOS devices, are very sensitive to small overloads of voltage or current. In some cases, a voltage spike no larger than 0.3 of a volt for a split second can ruin a MOS device.
These overloads can come from 3 main sources: electrical, electromagnetic, and electrostatic. We'll take the electrical ones first and look at a typical work situation. The board is in contact with a desoldering tool. It's connected to a power supply, which in turn is connected to the main source of electric power. There's a direct physical connection all the way through the system, and spikes appearing in the power line or generated in the equipment can pass straight through into the board and component. In the equipment, switching loads on and off, such as motors and transformers, can be a major source of the problem. If your equipment is switching these loads, you need to be sure the equipment incorporates zero power switching methods to prevent spikes from being generated.
Another source of the problem can be the power line itself. Brush motors, relays, and any non-zero powered switching equipment may be connected to the line somewhere else in the building. They generate spikes and could be injecting them into the power system.
They come down the line, pass through your equipment, and right into the board, even though your equipment has zero power switching. The place to stop this is back here, between your equipment and the power line. And the way to do it is by putting the proper filter between the two. Even better, and if possible, prevent the power line from becoming contaminated in the first place.
Positive grounding is one of the key methods for preventing electrical damage to sensitive components. Make sure first that your power system is a 3-wire one with constant polarity.
Then, check to be sure that the tool selected uses a grounded tip and is plugged into a power outlet with proper grounding and polarity. In some situations, you may also want to positively ground the workpiece. A separate grounding of the work may not be as safe because the 2 grounds could be at slightly different potentials.
Effective grounding also eliminates the possibility of a voltage leak from the tip of the soldering iron because of improper shielding of the heater circuit.
What's common to all these electrical problems is the physical connection that exists between all the elements of the system. And we can eliminate these problems by zero power switching, by grounding, or filtering, or by eliminating spike generation at its source. Another form of energy that may cause damage is electromagnetic. It's a field of energy, one that travels through space and makes radio transmission possible. The closer the receiving antenna gets to the transmitter, the more energy will be induced in it. An important characteristic of this type of field is that it's a ground-referenced one, and because of this, if you ground the receiving antenna, no energy will be induced. In our work, we have a similar situation. A transformer in the equipment may be acting like the transmitter. There's a fluctuating magnetic field around it, sending out energy. A soldering or desoldering tool can act like a receiving antenna, picking up the energy and carrying it right on into the work.
The way to prevent this, as we've seen, is simply to ground the tool. Then no unwanted energy will be induced into the system.
The third form of energy that can give us trouble is electrostatic.
And the problem is not one of giant sparks. Just by handling this innocent-looking plastic cup, I've now built up a charge on it big enough to ruin a MOS device by even approaching its leads. If we could see these charges, somehow make them visible, they'd be a lot easier to deal with. We can't actually see them, of course, but we can use a static meter to detect them. Watch the needle as I bring the cup down. At this distance from the meter, the needle indicates a charge of 500 volts. Less than 60 volts could ruin a MOS device. Virtually all plastics, unless they've been specially treated, are static generators.
This includes the plastic bags often used for shipping and handling conventional ICs, plastic foam and solder suckers, paper, plastic notebooks, and polyester clothing. They all can generate the charges.
But since they are non-conductors, you rarely get a destructive discharge directly from them. What happens is that they induce a charge at a lower level on a nearby conductor. And sweaty human skin is one of the most important ones for us. We've all been zapped after our shoes have brushed across a carpet and then we touch a metal doorknob. Replace the doorknob with the metal of a PC board, and the board gets zapped the same way. Preventing the damage is fairly simple. It consists of setting up a static-free workstation, like this one.
Note first the sign. It tells anyone approaching about the danger. Boards and assemblies are kept in anti-static bags at all times, except when they're being worked on. The work surface has been covered with a sheet of anti-static material that has been connected to a common ground. A number of commercial materials are available with conductive, non-conductive, or other characteristics from which you can choose to best suit your purposes. The operator wears cotton clothing, preferably with short sleeves. And most importantly, she wears a conductive wrist strap that's also connected to a good ground. Its purpose is to drain off all static charges on her skin before they can build up to a damaging level. Thus, the fingers or the skin will have no charge. The strap itself is insulated and contains a 250,000 ohm resistance that protects the operator from shock if she accidentally contacts a live circuit. When handling static-sensitive components, they're picked up only by the body, never by the leads, and never allowed to come near or contact any ordinary plastics or textiles. The anti-static tabletop and the wrist strap are the two basic permanent elements of any static-free station. Where these are always used, conductive floors and chairs usually become unnecessary, since their only function is to ground the skin. In some cases, you may want to consider the use of a device that ionizes the air. When static-sensitive assemblies are not in anti-static containers, they're referred to as naked. They must not be touched by ungrounded personnel or even approached by common plastics or textiles. It is best to remove sensitive components from their protective bags only on a static-free work surface. Plastic solder suckers should never be used here, since they can generate static charges of up to 5,000 volts.
The static problem, then, requires a number of preventive measures of its own, in addition to those for the electrical and electromagnetic problems. You need to be aware of all of these sources of damaging energy whenever you're dealing with sensitive components. Eliminate them when you can, and when you can't, protect the work against them.
This completes Lesson 8 in the PACE course on Rework and Repair for Electronics.